Alright, air brakes introduction. Discussion. Fasting Westerly Highland Railroad uses vacuums. You may wonder why a section on the air brakes is included in this presentation. There are two reasons. One, air brakes are more efficient than vacuum brakes and can be adopted in the future. Important to understand that there are various air brake systems. They work in very different ways. Therefore, it is to be any feature of the debate of the subject is worth having the background knowledge of the available systems. Many of the Festing Long Welsh Highland Railway crew visits railways with air brakes such as Nearby Valve, Redoubtable, and Talalin. The following slides are hopefully given an appreciation of operation characteristics inheriting the various types of air brake systems. Air brakes. Air brake cylinders generally operate up to 55 psi gauge pressure, this means that the air brake system has 5.5 times as powerful as a vacuum brake system, which has 10 psi gauge pressure. However, that does not mean that does not mean that you get more brake force. Instead, same brake force can be achieved using small brake cylinders. Return spring brake release, brake applied. Air brakes discussion. As the air brake cylinders are small, the piston head does not have enough weight to be arranged to move the blocks away from the wheels. The brake cylinders are fitted with a return spring for this purpose. This means air brake cylinders can be mounted horizontally, whereas vacuum brakes have to be mounted vertically. High pressure difference due to the air brake system gives a much faster propagation rate, so the response time of the air brake system is noticeably quicker than a vacuum brake system. Alternative. The diagram represents the George Westinghouse first air brake system. Steam-powered pump used to generate compressed air with stored reservoir on the locomotive. To apply the brakes, the driver control valve allows the air to pass along the brake pipe into the brake cylinder. To release the driver control valve exhaust valve. The release of the driver's control valve exhausts the air from the brake pipe to surrounding atmosphere. Shows the main reserve in the brake cylinders and brake cylinder and brake pipes. The brake cylinders. Air brake answers. The system is not a fail-safe in the event of the coupling brake. As air enters the system, the brakes of the front of the train will apply first, causing the vehicle to run into each other. Same is true of vacuum brakes described previously, but effects tend to be the worst with the air brakes due to the speed in which air fills the first brake cylinder. On long train and rearmost brakes could be deficient. As more brake cylinders are filled with air, the reservoir pressure falls. This means that the air pressure could become deficient by time all the brake cylinders of the long train have been filled with air. To solve the above problems, George Westinghouse reconfigured his air brake system as shown in the next slide. Alternative. The diagram represents George Westinghouse automatic air brake system. Air is now supplied along the brake pipe in blue to release the brakes. While releasing the brakes, auxiliary reserve on each vehicle are charged with air. To make a brake application, brake pressure is reduced. Shows the main reservoir, auxiliary reservoir, triple valve, and brake cylinder, and then auxiliary reservoir, triple brake cylinder, brake pipe, auxiliary triple valve, brake cylinder. Remember, the blue is now supplied to release the brakes. Air brakes. Answer. The brake pipe pressure is reduced. Triple valve automatically uses the air previously stored in the auxiliary reservoir to pressurize the brake cylinder. The system has required brake power ready and stored on each vehicle. Brake propagation is fast because the driver control valve only has to empty air from the brake pipe to make the brake application. Following slides illustrate the air brake equipment as fitted in some of the British trains in the air pre-grouping through the 1950s. The triple valve system. Triple valve system. The system is equipped with fitted trailing vehicles circular 1890 to 1950. Shows the auxiliary reservoir, triple valve with ratchet, triple isolating, valve cock, coupling cock, brake pipe, brake cylinder, coupling cock. Triple valve system. When the system is first charged, the air brake is released. Air pressure passes through the brake pipe and fills the auxiliary reservoir. When the brake pipe is reduced, the air previously stored in the auxiliary reservoir is directed to the brake cylinder. Triple valve system. This equipment is fitted to locomotive 1890 to 1950. We're going to zoom in a little bit. Shows a steam stop valve, air compressor, governor, automatic drain valve, exhaust air compressor, equalizing reservoir, brake valve, isolating valve, reducing feed valve, duplex pressure valve or gauge, driver's brake valve, release valve, and then brake pipe, coupling cock, dummy coupling, main reservoir, auxiliary reservoir, brake cylinder, triple valve bracket, triple valve isolating cock. Alright, the steam power charges the large main air reservoir. The driver control valve air allows brake pipe. The driver control allows air into the brake pipe. The purpose of the equalizing reservoir is yellow as described later. Locomotive air brake is applied in the system as trailing vehicles. A release valve on the cab permits the locomotive air brake to be released when on shed. Air brake, steam powered pump. Steam powered pump can be arranged automatic, semi-automatic in its operation. Automatic, the driver opens the steam valve, leaves it open, and the governor leaves. The device automatically turns off the steam supply to the pump when the main reservoir nears its maximum pressure. When the main reservoir pressure falls, the governor turns on the steam supply to recharge the reservoir. Semi-automatic, no governor. The driver only partially opens the steam valve to try to obtain balance. As the pressure builds up the main air reservoir, it provides increased back pressure on the air pump piston. If the steam valve is only partially open, the number of strokes of the steam piston is reduced near to the maximum air pressure. When it's balanced, the rate of pumping is just sufficient to overcome leaks, and the brake system continued. Steam-powered pumps continue. Regardless of whether the pump automatic, semi-automatic, the main air reservoir must be fitted with a relief valve, safety valve. This will prevent the reservoir from becoming overpressurized due to either failure of the governor valve automatic system or if the driver has opened the steam valve too far semi-automatic. Auxiliary reservoirs of trailing vehicles are not generally fitted with a relief valve because the pressure cannot exceed the main air reservoir. In addition, some systems have the pressure-reducing valve between the main air reservoir and the driver's control valve. Direct air brake valve. As vacuum brakes of the train air brake system supplemented with an independent locomotive brakes, the direct air brake valve takes a direct from the main air reservoir brake cylinder via the independent control and then double check valve. There were also versions of the Gresham Craven steam brake valve that enable the steam braked locomotives to work in harmony with the air brake trains. Triple valve system. The triple valve system, the key to device in George Westinghouse automatic air brake system is a triple valve. With the following slides, examples of operating the triple valve. To begin, consider and simplify the triple valve as follows: housing, plug valve, and piston. Moving the piston to the right will open the plug valve as shown below. Housing, plug valve, piston. Connecting the relevant equipment, the brake cylinder, auxiliary reservoir, no return valve, and the next few slides show the brake pipe. The next few slides show the operation, charging the brake system, and applying the brake. The brake pipe is charged to 70 psi. The piston is pushed firmly to the left, closing the plug valve to the brake cylinder. And then an auxiliary reservoir. Auxiliary reservoir is charged via the no return valve until the pressure equals that of the brake pipe pressure around 70 psi. The pressure is equal on each side of the piston. However, due to the piston rod, the force is slightly greater on the right hand side, keeping the plug valve shut. A brake application is made by reducing the brake pressure, for example, down to 60 psi. The pressure is now greater on the left hand side of the piston, and the plug valve is forced open. Air passes the auxiliary reservoir through the plug valve into the brake cylinder. The auxiliary reservoir pressure falls and the brake cylinder pressure rises. When the auxiliary reservoir pressure has fallen slightly less than the brake pipe pressure, the piston is pushed back to the left, closing the plug valve. And then by virtue of the small side of the brake cylinder pressure will reach around 25 psi for a 10 psi reduction in auxiliary reservoir pressure. Air brakes. Triple valve. To increase the brake force of the drive, but it can make a further reduction brake pipe pressure, say 60 psi down to 55 psi. Auxiliary reservoir will give up most of its air to the brake cylinder. Eventually, increase of the brake demand will result in the auxiliary reservoir and the brake cylinder pressure equalizing around 50 psi. This also allows what happens if the brake pipe is completely vented. Note that engineers have to select the correct size of auxiliary reservoir to suit the brake cylinder size on each vehicle, so that each vehicle on the train will give the same maximum brake force. Too large of a reservoir will give the too high brake cylinder pressure. The air brake system is very efficient because the brake pipe only needs to reduce 20 psi to obtain maximum brake cylinder force. Question: what is the problem with a simple triple valve illustrated above? Answer: there is no means of releasing air from the brake cylinder. The actual triple valve has a slide valve to enable the brake release, as shown on the next slide. The triple valve auxiliary reservoir hook is connected to the piston slide valve. Slide valve has two passages, one for applying the brake and one for releasing. Brake cylinder, brake pipe, piston, and plug valve. Charge the brake pipe pressure to 70 psi. Auxiliary reservoir with the piston pushed to the left will piston air can pass around the edge V of the groove within the auxiliary reservoir. Brake cylinder, brake pipe. Okay, use of the groove instead of no return valve means the small function of the brake pipe pressure will not result in higher auxiliary reservoir pressure in the subsequent undesired applications of the brake. Brake pipe pressure is reduced to 60 psi. Auxiliary reservoir, brake cylinder, brake pipe. Piston moved to the right, allowing the air to through the plug valve into the slide valve, but it cannot go anywhere. The piston continues to move to the right until the hook engages with the slide valve. Auxiliary reservoir, brake cylinder, brake pipe. The piston now moves the slide valve until the auxiliary reservoir air passage lined up with the passage to the brake cylinder. Note that how the movement of the slide valve is isolated with the exhaust passage that previously connected the brake cylinder to the surrounding atmosphere. Auxiliary reservoir pressure falls into the slightly less than the brake pipe pressure than the brake pipe. The piston closes the plug valve but does not have the sufficient pressure difference to move the slide valve. Brake pipe pressure is reduced 55 psi to increase brake demand. The greater auxiliary reservoir forces the piston to move to the right of the opening of the plug valve and increasing the brake cylinder pressure. Auxiliary reservoir pressure falls to slightly less than the brake pipe. The piston closes the plug and valve to the new higher brake demand. Again, it does not have sufficient pressure difference to move the slide valve. Brake pipe pressure is recharged to 70 psi to release the brake, and the large pressure difference across the piston forces the slide to move to the left. The auxiliary reservoir, brake cylinder, brake pipe. The brake cylinder air pressure is vented to surrounding atmosphere. The extreme left piston uncovers the groove, allow brake pipe air pressure to recharge the auxiliary reservoir. Question: what are the two problems with the triple valve system? Answers: after making the initial brake application, the brake force can be increased. That cannot be eased, and otherwise there's no gradual release. If the driver will attempt to ease the brake, the rise of the brake pipe pressure would push the triple valve piston fully over and release all the brake cylinder pressure to the atmosphere. This would dangerously become the auxiliary reservoir can only recharge if the brake pipe pressure is fully recharged. Rate of recharging the auxiliary reservoir depends on the size of the locomotive main reservoir, the pump, the power of its pump, and how many vehicles that are in the train, the number of the volume of the auxiliary reservoir. However, the brake cylinder release takes place at a fixed time and generally how much quicker than recharge auxiliary reservoir. This means that after the brakes are released, auxiliary reservoirs will initially be unable to make fully effective the brake application. This phenomenon is known as exhaustibility. Discussion: if the railway uses the basic triple valve system, and must ensure that the drivers understand that the system cannot gradually release and is exhaustibility. Due to above, the system can be challenged to operate, particularly if the considered scenarios enter the terminus station and have made too great of an application of the brake. What to do? Is there time for a release or reapply, or can you stop short without causing an obstruction? It's probably these reasons the original Westinghouse brake system was not adopted during the grouping era of the Britain Railways in 1923 to 1947. Despite the negative points, any driver that would encounter the air brake system will notice the response is much faster than a vacuum brake system. Also, if the locomotive main reservoir is large and train short exhaustibility due does not tend to problem due to rapidity to which auxiliary reservoirs are recharged. Discussion. Final note about the system exhaust reduces the effectiveness of the brake. It does not make the brake immediately unless if the brakes applied relief is reapplied before the auxiliary reservoir have recharged, it will still be air pressure to pass the auxiliary reservoir to the brake cylinder. However, instead of attaining 50 psi maximum brake cylinder pressure, it will only now achieve 35 psi. If the process repeats, there will be less maximum brake cylinder pressure. Next time, maybe only 25 psi. Repeated several times, the brake system will eventually be drained out of air, but it does not happen with just first attempt. Alright, triple valve direct or driver's control valve. There is a simple type to the air brake of the rotary handle connected to the disc valve. The valve has 3-position release, lap, and apply. Rotary and disc valve shows the main reservoir and brake pipe. Air is supplied to control with the main air reservoir. The air passes to the chamber of the upper side of the disc valve. The pressure pushes down on the disc valve, prevents leaking. Main reservoir and brake pipe. When the control valve is moved with the brake release position, air passes through the hole in the disc valve, which is now lined up with the brake pipe passage. With the controller moved to the brake apply position, internal passage of the disc valve connects to the brake pipe and surrounding atmosphere with the main reservoir supplied is isolated. Internal passage, main reservoir, brake pipe. In the lap position, the brake pipe isolated with both the main reservoir and the surrounding atmosphere of the brake pipe pressure will be held with the current level except for the effects of the leakage, which are much less than vacuum brake systems. All early air brake controllers had a lap position speed of propagation of the compressed air, making it unpractical continuous type of the controllers. Only a few locomotives remain fitted with the basic control that described above. Most are fitted with slightly more sophisticated versions shown over leaf. We'll probably recognize the control of this controller from many textbooks. It's connected to a small equalizing reservoir. It has an additional valve, the equalizing reservoir, main reservoir, and brake pipe. So, what are the additional valve and the equalizing reservoir for? The best explained first consideration basic type of three-way valve. If the train length would be increased, the volume of the air brake will also decrease because it is shorter. Therefore, by making some brake applications with a shorter train, we require the driver to open a control valve for less time. This means that the controller will feel differently depending on the length of the train. It is misjudged that the driver can make this most severe application that would have desired and explained previously exhaustibility of the air brake system could make air difficult to correct. With more sophisticated control of the normal application of the brake are made with the equalizing reservoir, the additional valve, adding additional valve with the automatic, the driver would only have to operate with the rotary handle as before. With the equalizing reservoir, fixed volume, regardless of the train length, the equalizing reservoir is charged with the same pressure of the brake pipe when the brakes are released. The additional valve is a relay valve. The normal surface brake applications are made with the air released with the atmosphere from the equalizing reservoir. The relay valve replicates the pressure drop into the brake pipe. The next few slides will illustrate. Air pressure from the main reservoir into the top of the controller. The pressure pushes down on the disc valve that prevents leak. Equalizing reservoir, main reservoir, and brake pipe. With the control brake in the release position, air brake passes through the disc valve with the brake and pipe of the equalizing reservoir. The brake pipe equalizing reservoir are charged around 70 psi. The relay valve piston is equilibrium with the same pressure each side. Due to this position, rod slightly more force over the upper side keeps the plug valve shut. The brake application is made moving the handle with the apply of the lap position only with the equalizing valve pressure of the reduced of the disc valve. The air escapes from the equalizing reservoir to the atmosphere passage of the disc valve. The relay valve piston becomes unbalanced. The greater pressure in the brake pipe lifts up the piston. Brake pipe pressure is relieved the atmosphere via the relay valve. The brake pipe pressure escapes the atmosphere. The brake pipe pressure equals the equalizing reservoir that the relay valve closes automatically. With the type of the control of the field of the air brake control is always the same in regardless of the length of the train. Movement of the control of the handle of the releases from the equalizing reservoir of the relay valve automatically replicate with the pressure drop of the brake pipe however long it takes. There's the one position of the control that is different from the emergency brake position of the dish valve that will all vent air directly with the brake pipe to the atmosphere to ensure the fastest brake application. As with simple control, the release of the brake will be done completely one attempt. There is no gradual relief of the air flows through the disc valve of the main reserve of the air brake and to the brake pipe. Main added reservoir is often arranged with a high pressure of 100 psi with the brake pipe release pressure of 70 psi with a make possible pressure reducing valve between the main air reservoir and the driver's control. Alright, your triple valve system overcoming the high drawbacks. Exhaustibility, no gradual release. The next few slides detail what they've done with the overcoming the problem. Exhaustibility, no gradual release with the inherent with the original Westinghouse automatic air brake system. Early attempts to solve the exhaustibility problem with the Westing triple valve with the mountain cock properly prior on the train operating over the route with a steep gradient. The crew would move the handle to the side of each triple valve. This redirected the brakes along exhaustion with the choke passes. The increased time of the taking of the air brakes will leave the time. Increased division of the air reservoirs will be recharged before the brake release is complete. Choose auxiliary reservoir, bring cylinder plane position and mountain position. Whether or not time delay with the division depends on the size of the locomotive main air reservoir and length of the train, how quickly the reservoirs take to recharge. Further, the triple valve mountain cock did not provide the ability to ease the brake gradually release, therefore it was not the ultimate solution. In Europe, trains operated with a tight time scale of the freight trains use the same line with express passenger trains. Therefore, it is decided that the air brake system would have to provide gradual release and exhaustibility with the achievement of the coming of rotation and the early 1950 introduction of distributor valve, which described fully in the next section. The distributor valve will be only allow the brake cylinder air pressure to exhaust into the atmosphere, but there's no air pressure for the auxiliary reservoir to recharge the brake cylinder to its maximum pressure. In other words, the auxiliary reservoir has to be recharged to permit the brake cylinder pressure to release. This myth of the modern pneumatic air brake system can be exhausted, but it's not true provided that all components are functional correct. No matter how careless the driver is with the control valve, the system cannot be exhausted air. Distributor valves will not allow it. Some of the very early promotional material of the distributor valves in the UK that define with a triple valve, some of the type of the subsequently logged over the national part of the database as triple valve. However, the triple valves are not used with the ultimate K, the UK mainline railways today. Incorrect definitions are worth bearing in mind. Some of the heritage railways do use the triple valve. The distributor valve comes with a compromise, releasing the brakes with a very long train. Most auxiliary valves take longer to recharge. If it leaves the situation, the driver may think that the brakes have also all released, when in reality, rearmost vehicles still have slight brake application. This is caused by the dragging brake at the rear of the train. If the driver has started to with the accelerator, but the dragging brake can cause the damage of heating wheels or by causing the wheels to slide on the rail. Later will lead to flats on the wheels treads. If for the reason the USA have never adopted for this reason the USA has never adopted the distributor valve system. In the USA, an improved system has been developed based on the triple valve system. The new system compromises two triple valve with two reservoirs. Auxiliary reservoir are used to apply the surface brake, while the emergency reservoir provides a backup source of air that can be applied to the brakes when the brake pipe pressure is reduced to zero. There are further refinements, including a valve with the use of the brake air cylinder to assist the recharging emergency reservoir. Housing containing two triple valves associated spool valves, known with simply with the control valve, the two reservoirs air usually controlled within one actual reservoir with a dividing wall. Improved system provides direct, quickly release, prevents them from being a dragging brake. However, the system cannot provide gradual release. The distributor system and the system. The next few slides illustrate the distributor system used throughout Europe and many other parts of the world. The distributor system is applied conventional train with the locomotive hauling trailing vehicles. For most part of the means of the freight train, the conventional trailing coaches. Modern multiple unit passenger trains use electro-pneumatic brakes, which are described in last section of these notes. The equipment is fitted with the trailing vehicle with the brake pipe, auxiliary, brake cylinder, distributor. Brake pipe to the auxiliary reservoir from the distributor. The distributing brake pipe is reduced. The distributor valve sends the drop to pressure auxiliary reservoir air pressure into the brake cylinder. Distributor valve is also a proportional valve that regulates the brake cylinder pressure and in proportion to the drop in the brake pipe pressure. When the brake pipe pressure is increased, the distributor valve uses the air pressure recharge with the auxiliary reservoir at the same time the distributor reduces the brake cylinder pressure, allowing it to exhaust in the surrounding atmosphere. The distributor will only allow air to exhaust with the brake cylinder auxiliary reservoir being recharged. The system of the driver can now easily brake gradual release. The distributor system and distributor valve. Distributor valve is complex with the component comprising over 100 parts inside it. Air valve with the control maximum pressure and initial emission brake pressure brake propagation and system release is beyond the scope of the notes explained by the distributor valve. Drivers of today's modern railway are not expected to understand the brake valve components, only how to operate the system. An exhaust schematic with a distributor valve that provided overleaf with the actual, with the only simple examples of the design include the limiting valve, the in-shot valve, the empty load valve, the variable load valve, passenger good, and changeover valve. Alright, distributor show with the auxiliary reservoir with the brake cylinder control reservoir, isolating valve, check valve, filling valve, equalizing valve, sealing valve with the main valve, the accelerating valve with the resetting valve with the release valve. Due to the complexity of the distributor valve, should only be the overhaul with the experienced supply of the overhaul with the test with the correct function of the special test rigs. The distributor is designed quickly to remove the replacement of the vehicle just 3 fasteners secured to the mounting bracket with all the relevant pipe connections. Therefore, with the running depot will simply change the complete with the distributor. If it gives a problem, will return to the supplier with the reference of the new distributor valve. The cost around 1,500 to 2,010 euros price of the valve. It requires overall 5 years at a cost of 250 euros. The distributor valve system is a good valve, very good system, but is also an expensive one. The distributor system driver the control valve. As for the distributor, modern driver control valves are complex. Again, beyond the scope of these notes of explaining all the functions, but for the reference control includes pilot valve, relay valve, overcharging valve, sealing valve, the emergency application valve. Driver control valve, the proportional self-lapping valve that handles rotated with one way to increase the brake pipe pressure, the other way to reduce the position of the handle with the corresponding pressure within the brake pipe, will maintain the pressure compensation for leaks. There are certain positions that are notched. There are running position and emergency position. The move handle with the running position with the initial application of the brake requires the handle to push and the handle to be pushed past the notch in the mechanism. This enforces the initial drop of the brake pipe pressure around 4 psi for the purpose of which ensure the distributor valves are activated successfully. Although the driver control valve is very useful, usually friendly with making the normal brake application. Several the system requires additional knowledge of the part of the driver. The distributor working memorizing brake release pressure in the chamber of the known as the control reservoir. To compare the pressure for the reduce of the brake pipe is to obtain pressure drop that has been made. However, there is a problem because not all locomotives will give the same release pressure. It's nominally 72 psi, but on any given locomotive it could be as high as 74 psi and low as around 69. When a locomotive is uncoupled with the train, the distributor retains release the pressure locomotive in the memory and with the control reservoir. The next locomotive with the coupled on until the train cannot generate as much release pressure, 70 psi opposed to 72 psi, the driver will not be able to fully release the brakes. Distributors can reset the operating brake release cords on each vehicle that have the time consuming these two methods of the remotely resetting of the brake of the system had been devised. One is known as overcharge, the other known as control reservoir dump valve. Overcharge, sometimes referred to as high pressure release, the preferred of the method of internationally Union Railways, or UIC. The driver control valve has a release position adjacent to the running position and coupled with the new locomotive of the train when the driver places the control valve in the release position. This charges the brake pipe pressure to 80 psi. With the pressure of the gauge settled for the driver to return with the control of the running position, it will have taken several minutes for the distributor to reset themselves to the normal brake pipe pressure at the over the locomotive 69 to 74 psi. During this time, the driver should avoid making brake applications because the distributor will memorize the excessive pressure, and the process will have to be repeated. Control reservoir dump valve. On some railways, the Irish Railway, in special case UK, the locomotive is not provided the means to overcharge brake pipe pressure. Instead, each distributor is fitted with a control reservoir dump valve. The valve automatically reduces the pressure in the control reservoir when the brake pipe pressure is reduced to zero. In other words, placing the control in the emergency position reduces the memory pressure, and the distributor reduction will not affect the emergency application because the pressure drop is still well as excessive as what is required. However, when charging the brake with the emergency position, the locomotive will pick up reduced brake pressure and then take it up to the one of the specific release pressure for the brake is reset. Operational system is straightforward. Whenever the charging the locomotive with the brake pipe is empty, the resetting of the brake is automatic. The only note of caution is that partial brake release cannot be made after the emergency brake. Subsequent to normal brake application with a deficiency, the brake must fully release after the brake has been zero pressure. Alright, twin pipe system overview. In summary, the disadvantage of the distributor system is that the brake release is delayed if there is an insufficient supply of air pressure relief of the auxiliary reservoir at the same time period. On long trains, that can lead to dragging brakes in the rear of the train that might be unnoticed by the driver. The problem overcome with a twin pipe system. It is in this system the auxiliary reservoir starts refilling the moment the brake application is made. The refilling is made possible with the second pipe known as the main reservoir pipe, which connects the locomotive main air reservoir directly to all auxiliary reservoirs. This next few slides demonstrate the two-pipe system. The twin pipe system fitted with the trailing vehicle with the main reservoir, the brake pipe, the auxiliary reservoir, the distributor, and brake cylinder. There's a two-pipe and twin pipe system. The system charged with the air brake pipe and the main reservoir pipe, charged with the air reservoir, the main reservoir, brake pipe, non-return air auxiliary reservoir, brake cylinder. Auxiliary reservoir can be charged either the brake pipe, either the distributor, the main reservoir, either the no return to the valve. When the brake pipe application is made, reducing the brake pipe pressure air from the auxiliary reservoir is submitted to the brake cylinder. The auxiliary reservoir immediately starts to refill the air with the main reservoir pipe. The breakers release the auxiliary reservoir are already full of air through only volume of the air brake, therefore only the volume of the air in the brake pipe needs to be refilled. The increase of the brake pipe pressure instructs the distributor to release air from the brake cylinder to the atmosphere. The twin pipe system can be operated with the main air reservoir being connected with as shown below. The main reservoir, brake pipe, auxiliary reservoir, brake pellet, distributor. No return valve prevents auxiliary reservoir air from escaping the main reservoir pipe. In single pipe mode of the auxiliary reservoir is recharged via the brake pipe as within the single pipe system. Twin pipe system. This is an important point to be made about the use of the isolation of the main reservoir pipe. Traditionally, when working with a twin pipe mode, the auxiliary reservoir charged around the 100 psi maximum because it's supplied with the main air reservoir, not the brake pipe. This makes brake application quicker, the high pressure flow faster through the distributor. Therefore, the system main reservoir pipe must be either connected with the whole train or none of the train. Lastly, interoperability. Steering does not require the pressure-producing valves to ensure that the brake application speed is the same with the vehicle on single and twin systems. It may appear that twin pipe system ultimately pneumatic braking for the railway vehicles. No, not quite so, because twin pipe work brings a new hazard which is known as crossfeed. Now that the main reservoir pipe also always charges the high pressure air, even during braking, a single valve failure in just one distributor of the train can permit air to flow over the main reservoir pipe into the brake pipe. This supply of air is the crossfeed will fight driver's attempted reduction in brake pipe pressure. Dangerous situation. A failure in the distributor permits main reservoir pipe air pressure to crossfeed in the brake pipe. The brake pipe pressure does not reduce and no brake application is made. Designers try to ensure the supply of the air from the locomotive main air reservoir is sufficient to be beat with the rate of each driver control valve with the empty air from the brake pipe. To do this, chokes are sometimes fitted between the main air reservoir and the main air reservoir pipe. And hose coupling main air reservoir internal check valves. This ensures that the air cannot flow with the main reservoir pipe with the brake pipe. In the event the pipe becomes being incorrectly connected together that prevents of the crossfeed, only if the two main reservoir hose couplings are placed together and are integral checks valves force open. Irish Railway used an alternative, arguably more fail-safe solution. The main reservoir pipe hose couplings are deliberately a different size so that they won't connect to the brake pipe housing coupling. Alternative is Vale of the Rydal Railway and Curley's Light Railway. Alternative to the traditional railway air brake system described previously are generally quite expensive to install, but they contain many refinements that enable you to the high-speed trains up to 125 miles an hour, long freight trains up to 2,000 tons in the UK. On heritage railways operating 25 miles an hour, such advanced system is not necessary. The number of independent railways have developed their own air brake system that makes this commercially available to specialist air valves and fittings. A couple of examples are illustrated in this section. Example 1, the valve rehaled railway. The valve rehaled out air brake, twin air brake, service pipe, and emergency pipe. The system is charged with the air emergency pipe is feeded into the auxiliary reservoir on each vehicle. Main reservoir, emergency valve, brake valve, reservoir, brake pipe, service pipe, emergency valve. Normal service of the application may be the operating drive of the brake valve that actually direct the air brake valve. The emits air from the main air reservoir into the service pipe, which leads directly to all of the brake cylinders via the automatic relay valves. When released, the air brake is discharged to the atmosphere of the drive of the brake valve. The normal operation system is straightforward to direct air brake to all the vehicles. An emergency air is vented through the emergency pipe of the relay valve, since the lost pressure from the receiver to short air pressure from the auxiliary reservoir into the brake cylinders. Air brake system used with the valve of the Rehottle Railway. Same problem with the vacuum brake with the fasting Westling Highland Railways. Air pressure and surface pipe into the brake cylinder with the front of the train and before the rear with the potential causing coupling to jolt if the brake application is severe. However, speed of the operation while is a simplified air brake system has provided acceptable permitted use commercial available for air fittings and valves. This provides a considerable cost saving over equivalent specialist railway braking equipment. Question: what is the fundamental difference between valve Rehobb's air brake system and conventional railway twin pipe system? Answer: the valve Rehob, both air brakes must be connected. One of the triplet of the brake for the only one of the emergency brake. One second pipe, there can be no brake continuity. Conventional railway twin pipe system can be operated with a second pipe, the main reservoir pipe, if the brake pipe provides the brake continuity as well as the service brake. Example 2 shows the Kirklees Light Railway. This is possible simple the type of the railway air brake system compromises applied air pressure release for the brake cylinder connected directly to the brake pipe. So the main reservoir, brake valve, brake pipe, emergency valve, and piston. To release the brake's air pressure is admitted to the brake cylinder to overcome the spring force to apply with the brake air is vented with the springs apply the required brake force. Spring-applied air pressure release brakes are not popular in miniature railway. Release brakes are popular on miniature railways and inherently fail-safe. Springs mitigate the spring mitigate the need for stored air pressure, therefore double up parking brakes. No separate handbrake is required. However, a system is relatively basic. It can be difficult to retain the same spring force in different vehicles. For example, the spring can give less force as they extend, so a vehicle with worn brake blocks, greater slack in the system will be subject to less brake force. Air versus vacuum summary. The following slides a list of the general advantages and disadvantages of air vacuum brakes. Useful summary of the main points. However, the previous section of these note for the demonstration of the actual numerous different types of air brake system. Each different type has relative advantages and disadvantages. Air versus vacuum. Air brakes, high pressure, energy efficient, fast propagation brake, great control. Air pump, many moving parts, requires more attention. End cuts cause hazards, and typically superior vacuum brakes. Low pressure, susceptible to leaks. Slow propagation of brake requires driver anticipation. Injector, no moving parts, high reliability, no isolation. Cox inherently fails safe, ideal for heritage lines. EP brakes overview. Air versus vacuum. As a conclusion, we know the principle of the modern electro-pneumatic brake is described. The illustrative of the start of the air in terms of passenger train braking will provide reader with the appreciation and historic nature of the vacuum brake system. Vacuum brake technology used in the Fessling Westall, the Highland Railways dated in the 1930s, perfectly acceptable for the use in today, but compared to the state-of-the-art brake system, requires more driver skill to obtain optimal performance. The EP brakes show the power brake controller and the brake gauge. These cabs are the turbo starter diesel multiple unit, also known as Class 170. There's a combined power and air brake control. The only one brake gauge indicating the main reservoir pressure and brake cylinder pressure. The power brake control with the electrical device, both with the power and braking of the trains controlled electrically instead of pneumatic brake pipe. These are control wires. These main reservoir pipe that charge with auxiliary reservoirs. Braking is controlled in fixed steps. Step 1, initial light brake application. Step 2, incremental increase of the brake force, and so on. The next few slides illustrate least surface brakes and emergency brakes. EP brakes, brake release show the main reservoir, EP valve, reservoir, piston, gauge, battery controllers, locomotive main reservoir, car control wires, EP reservoir, controller sends electrical signals on, control wires are alive to release the brake. Controller drops out of the electrical signal with the EP valve responds by admitting air into the auxiliary reservoir to the brake cylinders. All the electrical signals are lost and turned off. The EP valve responds with the maximum pressure to the brake cylinders. The advantage of the EP brake system is electrical signals travel much faster than compressed air, therefore making a brake application. All train brakes will be applied instantaneously. This is true whether there are just 2 cars or 12 cars on the train. exclusion summaries, air versus vacuum. Hopefully the above has been usefully insight with the train brake system and their components, parts, operation. After so many slides in the span, it may be tempting to consider above as comprehensive, but there's much more the subject of the train brakes. Final slide lists some of the topics that have not been covered in these notes. Modern brake equipment: empty loading, brake loading, proportional brake, hydraulic, pneumatic brakes, good passenger charging over time, application release charging, EP brake methods, hardwiring, multiplexing, wheel slip protection, brake rigging, class brakes, pusher brakes, disc brakes, and slack adjusters. Alright, that was air brakes introduction PowerPoint.